Sebastian. The next speaker is Alejandro Bernabeu. Alejandro Bernabeu is going to talk about three footbridges. He's a PhD in civil engineering from here, and he specializes in singular buildings. He has about 15 years of experience, and he has been working in the past in IDOM, and is now in his own engineering consultancy companies. And let me say that he has won in this year, 2015, the IAPSE prize. So congratulations, and also the prize, the Spanish prize for outstanding young engineers from our institution. So Alejandro, it's up to you.
Well, good morning. I want to thank the organization committee for inviting me to participate in this workshop on bridge design. I have borrowed the title of my presentation from Charles Dickens' A Tale of Two Cities, in part because of its famous opening lines that could easily apply to our current social, architectural, and engineering situation. Nowadays, it is also the best of times. It is the worst of times. It is the age of wisdom. It is the age of foolishness. It is the epoch of belief, and it is the epoch of incredulity. But also I have borrowed the title just because the purpose of the presentation is to openly narrate the design process of free footbridges, considering the design criteria as well as the main technical issues. A particularity of these free projects is that they have all been done in collaboration with the same architects, Ginés Garrido and Francisco Burgos. The first project, the first footbridge, is located in Madrid and takes part of the huge urbanistic operation of Madrid-Rio, all along the Manzanares River through the city. And when this project was designed, a number of most of the operation was already under construction, and in particular a number of very singular and interesting footbridges, like the twin concrete shield footbridges, the big spiral footbridge, or the Y footbridge. And this is the location of the new footbridge. So with this context, and considering also the criteria of ease and rapidity on construction, and economic restraint, we proposed a very simple solution, a straightforward solution that the purpose was almost to be unnoticed, as if the footbridge was already there before the operation was done. So the footbridge is just a 43-meter span, straight line, just with a very uncomplicated structure formed just by a couple of plain web steel beams located at both sides of the deck and that serve also as handrails. It is a minimalistic solution in terms of composition, but just with a couple of key aspects, which is the slowly varying width of the footbridge and the location of the stiffeners that are seen from the outside, from the exterior, with the underside edge-free. That marks a rhythm of the structure as well as a kind of discontinuity and vibration. A small tribute also, as well as the pale green color of the footbridge, to the fantastic German bridges built after the Second World War, as the Colonia Deus Bridge from Leonhard and Andra, or the Cardinal Fritz Bridge. The construction process was very simple. The two beams came directly to site, and they were directly set with the help of two cranes. And the footbridge finally opens in 2009. After this project, we decided, together with the architects, to present a proposal for an international competition for a new footbridge in Maribor, in Slovenia, over the Drava River, covering a total length of 120 meters. The most important aspect of the location for the new footbridge was its closeness to the Stary Most, or the old bridge of the city, which is a free-span steel arch bridge. We decided not to compete with the existing bridge, but instead of that to value it. proposing a bridge which was very close to the water level, not a big structure, and mirroring the free spans that the existing bridge had. So we proposed a continuous band with this same structural, very similar structural configuration of a double steel beams. In this case, the shape was adjusted of the beams to form a continuous deck that it was covered with wood. And technically, it has no very much complication, only dynamic aspects that will be commented forward, as well as the same principles with the Princesa footbridge. Interesting issue was related to the design of the piles that was proposed to be as delicate, as transparent as possible to maintain the continuity of the deck. In this sense, we proposed a set of thin steel tubes that are inclined in an apparently random composition, but are actually related in some sense to their structural requirements. 4 of these steel tubes are located on either side of the deck, so they can directly support the vertical load that comes through the steel beams, while the other 3 are located in the center area of the deck and are much more inclined, so they are able to directly assure the lateral stability of the footbridge. Here we have an image of the proposed footbridge, where we can see the transparency of the proposed intermediate piles, as well as the continuity of the deck. The proposal was awarded with the first prize, and the project was developed, but unfortunately, it remains for the moment unconstructed. As I said, the main technical issue of these 2 bridges was related to their dynamic behavior and control of vibrations. There are middle span steel footbridges between 30 and 50 meters. They are all in the range of the same frequency, which falls well beneath the range of frequency that are excited by walkers, by the step of pedestrians. In this sense, carefully analysis was done, and furthermore, together with Victor Marker, which is a well-known Slovenian engineer with whom we collaborated in the Maribor project, we developed a research in this sense, together with these 2 footbridges, as well as 2 other footbridges he has recently built, also in this middle span steel footbridges type, which is the Studenci footbridge, also in Maribor, not far from the Lentabor footbridge we have seen, and also having a free span, which means 42 meters, and in this case with a triangular steel truss as main structure. The other footbridge is the Riba footbridge that span 25 meters in Ljubljana with a thickness of just 50 centimeters, which means a very slender proposal. This is an image of the 4 footbridges section, Studenci, Princesa, Maribor, and Rigia in Ljubljana. Width varies from 3.5 meters to almost 6 meters, a little bit more of 6 meters, while the height varies from just 50 centimeters of the Ljubljana footbridge to 1.7 maximum height in the Studenci footbridge. As I have said, the natural frequency of all these footbridges falls well in the range of 1.25 to, let's say, 2.3 Hertz, which means that they are likely to present dynamic problems caused by the excitation of walking pedestrians or joggers. This is the natural frequency of the different footbridges. This is maybe a little kind of special, this Ljubljana footbridge, since one of the supports is spin and the other is continuous with the abutment, which makes that the frequency increase. In this case, we're not in the frequency range of walkers, but in this of joggers. So at the end, the problematic was similar. So in this case, the vertical acceleration has to be calculated in order to check, to verify if the accelerations obtained falls in the discomfort or in the comfort area. We can see here all these accelerations are well in the unacceptable area, and beneath between those 2 lines will be on the bearable area. And this is the acceleration obtained for walkers. So we can see this one, the Ribja footbridge in Ljubljana, is okay for walkers, but I have said it was uncomfortable in the case of joggers walking crossing the footbridge. In all these cases, we proposed a solution which is very typical in this case, that is to improve their dynamic behavior with the use of Tannet mass dampers. Tannet mass dampers, as you may know, are just formed by a mass, a spring, and a damper. The damper frequency is adjusted to a certain frequency of the structure. So when that structure is excited, the the damper reacts in a different phase, so the acceleration is reduced. Tannet mass dampers are very small in size, so they can easily be fitted into the structure. As I have said, it's quite an easy operation to improve the dynamic behavior in this case of medium span steel footbridges. The last project is actually a set of 3 footbridges in Toledo that take parts of the huge project of integration of the Tajo River in the city of Toledo that goes all through the river in the city. This is a view of the location that have to link the 2 river banks. One of them close related to the city, and the other much more rural and abrupt. There were several important criteria in this case. First of all, the 500-year flood level, which is represented here with this continuous line, was very high from the actual water level, so mean that the structural cost had to go quite up in this view. Another criteria is that we had to avoid to set piles in the river. We can see also in these pictures there is a very important difference of levels between the two banks. And also the river is not centrally located, but leaving an important area, an important length on the rural bank. In this area, piles could be set if desired. There was also an intention not to build a big structure, to remain as simple as possible and as close to the water level as possible, but of course respecting always the 500-year flood level. So considering all these criteria together, stress ribbon structures appears to be a good solution in this case. These are 2 outlines of one of the footbridges, the one with more length, which is around 140 meters. We consider the possibility to disposing an intermediate pile in this area, which will reduce the maximum span, and which will center the river on this span. But the thing is, there were 2 issues with this. First of all, stress ribbon footbridges, if we have 2 spans, the horizontal efforts have to be balanced in the intermediate pile, so we don't introduce horizontal efforts to the pile. And this means that with a very different length of spans, one of the spans will be almost straight, so you cannot feel this stress ribbon, this catenary shape. And the other one is that while this outline is continuous, here the pile introduced a point of discontinuity in the outline of the footbridge that we thought it will not fit with this idea of simplicity we wanted to highlight. So we finally decide to go for a continuous stress ribbon footbridge. As you may know, and we have been seeing examples on the presentation before, stress ribbon footbridges adopt a catenary geometry, which means that gravitational loads are transferred through axial efforts, meaning that the deck can be reduced to minimum. In this case, a key aspect of the 3 footbridges was to exactly choose the location at the outline of the footbridges, trying to minimize its maximum span, which we were already on on the area of maximum spans already constructed in this typology, which is a Japanese footbridge of 148 meters. Also to try to balance the different level on the two sides, as I have said, to respect this 500-year flood level. So this is the outline of the 3 footbridges, which, as you can see, each one is differently oriented to the river. In each case, adapting to its location and the particularities of each size. And here we have the outline of the 3 of them, with a maximum span that varies from 106 meters to 132 meters. Stress-driven footbridges were formed by a concrete deck formed by prefabricated elements that house a hose on both sides to house the lateral cables, and interior ducts that will house the post-tensioning cables. This is a typical section on the supports area, as we can see here, where important bending efforts concentrate. For the rest of the structure, just we only have axial forces, so the deck can remain as thin as possible. But in the supports, it has to be increased, so there were constructed with in situ concrete. This is an image of construction taken from the Sacramento footbridge from Jiří Stráský, which is a very well-known Czech engineer, which has built a number of these stress-driven structures. And as we can see, the construction process is first to set the lateral cables with an initial catenary geometry. Then the different prefabricated elements are set, hanging from these cables. Afterwards, the joints are concrete, as well as the lateral supports. During all this process, the catenary geometry evolves, meaning the catenary shape varies. And since the structural behavior is directly related to this geometry, this means that an evolutive non-continuous analysis has to be done. And this is the final shape of one of the footbridges, the one with the longest span. And we can see here another important issue of this kind of structure, as we can see in the abutments. And since all the gravitational loads are transferred through axial forces, and the slope of these catenary shapes are very small, this means that a very important horizontal effort has to be transferred to the ground. Of course, the abutment solution depends on the ground condition, and in this case, it was very different from one bank to the other. On one of the banks, there was the granite level was shallow, so the load transfer could be done directly through post-tension cables anchored on the ground. On the other side, however, the granite ground was much more deeper, and a set of inclined in both directions micropiles was set up. In this case, there is an important issue that there is a certain horizontal displacement caused because of the flexibility of this system of micropiles, and this horizontal displacement has also to be improved in the analysis. Just a couple of words to finish with this presentation regarding the analysis of these footbridges. Well, this is an image you can show us remain as close as possible to the water level, and we can appreciate the continuity of the shape. As I have said, it requires a nonlinear evolution analysis. This is just a table showing the different load phase, the state description, and which means that each phase depends on the geometry adopted on the level of effort adopted in the precedent phase. On the first two phases, where there are only the cables that are acting, and afterwards is the whole system, cables, structure, concrete deck, and post-tensioning cables. In the case of ultimate limit state, it is considered that the deck is cracked, so it's only the cables, in this case both post-tensioning and hanging cables, that assure the ultimate limit state. Here is just an image showing the concentration of bending efforts in the supports and the bearing and the flexion, which means bearing of the catenary geometry. In terms of dynamic analysis, it's also something to, of course, to be considered. But as we can see in this picture taken from Jiří Strack's book, this shows represent a number of stress ribbon structures, showing the frequency in hertz and the maximum acceleration obtained that all falls well beneath the maximum comfort level. The one in red is our footbridges in Toledo. Something similar we can say to an aeroelastic FS that has to be taken into consideration for, let's say, more than 100-meter spans. But as say for dynamic analysis, there is no report of problems of aeroelastic problems in these kind of structures, and the results falls well into the comfortable area. And so, this is how this tale of free footbridges comes to an end. Thank you very much.